I see a red light. Butch is on the air. Hi boys and girls, it's me Butch. My name is Terry David Silvercloud. I'll be 74 years old tomorrow. Today is the 23rd of October 2018. It's a Tuesday. Cloudy and cooler today. We've been having nice sunny weather. So to keep busy in my old age and kill time and be useful on the planet, I work on my art and still do a lot of photography. But one of my fundamental passions is physics. And the physics in which I take interest lies at the level of very fundamental reality, at the dark matter, dark energy level of reality, where the largest particle in which I take big interest is the electron. The people at CERN that smash atoms and stuff, they smash protons together. Protons are very large objects in comparison to electrons. So what was I going to talk about? I'm a bit ADHD. So today, I'm an atheist and I don't believe in an afterlife, so I want to make as big a splash as I can and make myself as purposeful as I can, since I was condemned to this barbaric rock of a planet to live a life. I'm old and experienced, and I want to try and get out some of my ideas. So this stuff I'm talking about, you can check it all out yourself, but it's on the level of theoretical physics. And probably, there's a mouthful, if you're watching this, you're into physics. I can't imagine why else you would be here unless you're trying to figure out who I am. Either way, you're welcome here. So, in my old age I'm into art, but I really took an interest in physics again more than 15 years ago when I asked myself a few what-ifs and had more time on my hands as I was becoming semi-retired. And one of the things I was doing 15 years ago or so, nearly 20 years ago now, was asking myself some fundamental questions like, what does it take to be here and there at the same time? In other words, from a point of view of relativity, where are you over there? Like objects occupy space, so if you're into physics, I think you'll get what I'm talking about. They are both here and there at the exact same time, at least for it. And in quantum physics, there's an issue where you can't quite talk about particles when they get really small, because you need to talk about wave motion and quanta and photons and stuff. And Schrödinger summed up the problem with his famous cat mind experiment, and if you're into physics you'll know what I'm talking about. Schrödinger's cat. You can't know everything about something at the same time. You may know one thing, but you can't know the other. If you know one, you can't know the other. So I'm trying to work at the level where I've lifted up the box to see what the H is going on under that box, and if the cat is alive or dead, and if you're into physics, you'll know what I'm talking about. So I was questioning all these kind of things, and I came up with a very simple answer of what it takes to be here, there, and everywhere within any given sphere, within any given time, or a time reference with which we would be familiar, one based on our time. Not absolute time, but, I think you know what I'm talking about. Time, measured in seconds and all that kind of stuff. As we perceive time at our size. Time is related to how big you are. If you lived on a carbon atom, a week would be years to you. That's a long time if you're that small. So for the size of us, we humans, who are virtually non-existent in this universe. We are so small, and we live for just such a moment in time that we barely exist at all. So I'm diverting here like an ADHD person usually does. Where were we? So the way you can be here and there and everywhere within a sphere at the same time is quite simple. All you have to do is be able to move faster than the speed of light. That could be tricky, right? And the exact speed you would have to be moving to fill the sphere everywhere all at once at the same time. If this was the box, pretend the box is now a sphere, and you want to be everywhere all at once within the sphere for a given length of time, you need only move at 4/3 pi c cubed. So the speed of light is set against a second, so for 1 second you need only exceed the speed of light by 4/3 pi c cubed, which is nothing more than the formula for a volume of a sphere, where the speed of light is the radius for any given time. It's a lot like Einstein's E equals mc squared, but all his math was linear, and he wasn't quite into waves, and then he had to think, oh right, in 1916 waves were all brand new, so when the whole idea of E equals mc squared came up, you're dealing with vector two-dimensional forces rather than three-dimensional energy, like what, this is where quantum physics comes in by, you can have a quantum of energy, which is basically a field, and more specifically we can describe things with fields within fields. That, I think you may know, if you're into physics, you'll know what I'm talking about. That's not important. So today, anyhow, way back then, besides coming up with that 4/3 pi c cubed thing, like what would it take to be here, there, and everywhere, and because I'm an atheist, and the reason I asked myself what would it take to be here, there, and everywhere was like, how fast would God have to move to actually be here, there, and everywhere, and because I'm an atheist, I ask all kinds of funny questions. But another question I was asking, because I was thinking about writing a book, was what if humans just evolved, but a life raft of aliens crashed here and did a little genetic upgrading, and stories of the Bible, the Garden of Eden, support that entirely. In the Garden of Eden story, humans were quite abundant by day 7. They were there before Adam, and then Adam was a special case who became sentient, and the whole idea is easy to generate a story that aliens came here for either by accident or on purpose, and use the existing humans as some kind of slave labor and attempted to upgrade them, apparently in failure or not, who knows. So at that time, because I was asking myself all these strange questions, is if aliens had been here and they knew they weren't going to survive, if they were like a crashed exploratory expedition from somewhere else in the galaxy, would they have not left some simple signs? And that led me to learning more about the Kaaba. The Kaaba is where all the Muslim folk go. Can you see it there? See, it's in Mecca, and it's this very, very, very ancient building to which Islamic types want to go once in their life and walk around 7 times and touch the black stone, which is some old meteorite from who knows when. The interesting thing about the Kaaba is it's a cube, and it's very ancient. According to the Quran, it was built by Abraham, and Abraham existed at least 2000 BC, 4,000 years ago. So that building is quite possibly one of the world's oldest stone structures, not as old as the pyramids, but old. The pyramids date to about 4000 BC. The pyramids were old in the time of Abraham, and the pyramids were certainly extremely old in the time of Moses. Moses lived around 1200 BC, so the pyramids would have been several thousand years old at the time of Moses, and they would have been old at the time of Abraham. So Abraham wandered around, and he may have been the one that found the black stone. Who knows? Nobody knows where it came from, but it's clearly a large meteorite, and a really big one. And it would have illuminated the skies, and a lot of people would have probably gone looking to see what this is all about at that time, and there was a lot of climate change issues going on. Who knows, maybe the black stone had something to do with the climate change issues that were happening, because Abraham was fleeing drought. That's why he was traveling around with his goats and whatever. So they built the Kaaba, which happens to be about 50 feet cubed, and the Kaaba has been rebuilt a few times, but it's still a cube. And in the time of Muhammad grew up there. His uncle was the caretaker of the Kaaba, and it was by the oasis Zamzam, which is a natural stream which still flows. You can buy a bottled water from Zamzam still. A lot of the main religion of the time were various pagan types of religions, and because many people were nomadic, if they had some religious relic, they could leave it at the Kaaba. So a lot of various types left their relics at the Kaaba, and it was a place where Abraham was said to have stood. So the whole point of this, it was a cube, and that was only interesting to me when I discovered that the Holy of Holies of the first and second temples were also cubes, and exactly pretty much the same size as the Kaaba. In the Bible, the Holy of Holies is stated to be 30 cubits by 30 cubits by 30 cubits, which is 50 feet by 50 feet by 50 feet. And why a cube in those days? That was hard to build, because you would have to get yourself some really strong lumber to make a flat roof. A 50-foot flat roof is no easy task, especially in those days. That was no mean feat to build a. It may not sound like much today, but a 50-foot by 50-foot building with a flat roof, that was a big deal 4,000 years ago. So you had to have access to very large timbers to do that. And in the first and second temples, we know that when the temple was built, the timbers came from Tyre. So I'm not going to get that, but I want to get back to cubes. And that got me studying cubes, which brought me to eventually asking questions about dark matter. But the interesting thing about a cube is the shape. Can you see that here? Where's my finger? Does that show up very well? If you look really carefully, the pattern for a cube is a cross. That just may be some weird coincidence. But what's also interesting is if you draw an X on every surface of a cube, the shape you will get inside of it is two interlocking tetrahedrons. And in the Jewish faith, it will be known as the Merkaba star. It's interesting that Merkaba incorporates the word K-A-B-A, which is the name of Kaaba, which is the house, or perhaps cube. I don't know for certain what Kaaba means. I don't know if anybody knows, but the point is the Merkaba star is a shape contained in any cube. If you just draw an X on every surface, you just outline the edges of two interlocking tetrahedrons, which two-dimensionally is the Star of David, you would call it, and three-dimensionally is the Merkaba star. So is this or is this not some ancient symbol? I don't know, but it certainly is very interesting. But what got more interesting for me, whether it was deliberate or not, was the mathematics of it all. And in pursuing all of that, I began asking myself questions about the fundamental nature of reality. And after many years of thinking and coming up with a lot of solutions in my own mind of how one could construct all of reality out of an infinity filled with only one substance which filled infinity, that is to say, the concept of emptiness, absolute nothingness, does not exist physically. That there is nowhere that is not filled with somethingness, and there's where your dark energy and dark matter comes into being. You know, as I wave my hands around, and I'm very demonstrative just by nature. I'm an artist. I'm old. I'm allowed to be wacko. You know, you're passing your hands through a gas, many gases, only a small percentage of which is oxygen. And oxygen is a very large atom. Weight-wise, it's actually heavy, and so is nitrogen and carbon. There's all kinds of things there, and you're quite happily moving through it. So that's not that big a deal. And when you get to empty space, it's best to empty your mind of the idea that it's nothingness. Radio waves are going through space with no problem at all, and physical objects are flying through space. So it's better to think of space as being some kind of fluid, which I'm going to call dark energy, and that the solid things are obeying the laws of buoyancy, where there is no up or down. Up or down will be determined by how much inertia you have, which will be determined by how much spin you have. So there's lots of different ups and downs all over the place, and where you are caught up within any amount of swirling going on the bigger picture of space will determine how much spin you're doing. And here on Earth, you think you're stuck to the Earth, but you're being pushed against the Earth. That's what I'm telling you. By forces trying to make your physical body come to rest dead center of Earth, because the point of least motion on Earth is dead center in the center of the planet. There is less motion there than anywhere else on the surface of the planet, and everything is trying to get there, because within the swirling of Earth through space, everything's trying to find rest. We are not going in neat circles. We are going on a helical paths through space. The sun and Earth and the planets don't have time to sit still in space and spin in nice, neat little ellipses. The whole shebang is moving with the galaxy, and if you could sit back and somehow be stopped, and you would see that if you plotted the path of Earth through space in a year, it would make one gigantic helix, which would be the wavelength of Earth for a year. You know, it would be, it would have a time of 365 and a quarter days, and the wavelength would be approximately 7 billion kilometers within the Milky Way. You have to remember the Milky Way is moving too. So technically speaking, it could be a longer wavelength, but more likely is that wavelength riding a longer wavelength, which astrophysicists would be inclined to call a gravitational wave. So all waves move at light speed, but things within atoms also move at light speed. So what defines light speed? And this is what this whole long yak is all about. I asked myself some questions about the electron a couple of years ago, and then it began to be obvious to me that because the electron occupies space, and for most practical purposes we know of is not destructible, nor does it change its physical size. It may change the space within Schrodinger's box that it is occupying within a given space of time, but the actual can only be made to spin faster or slower, or to move faster or slower. So to make one of these things move more quickly, we need only apply what we would call more voltage, but voltage is just pressure moving the actual electron through time and space. And the other thing it might be inclined to do is simply spin faster, or perhaps the net motion might be a vibration. So in direct current, the electrons are moving, but they don't have to move at the speed of light. If we have a wire and we have an electron enter it at one end at exactly the speed of light, a different electron will pop out at the other end in direct current. If it were alternating current, the electron need only vibrate or rotate more quickly to make either the adjacent electron or some intervening material which conveys energy at exactly the same amount minus, there's going to be a resistance here, minus a teensy little bit, and we will call that resistance over time. And the resistance in space seems to be extraordinarily low, but we can calculate it because by definition Ohm's law defines a given number of electrons passing a given point in 1 second, and we even have a number for what number of electrons there are. So if we had a wire that was just big enough for one electron, and it was how far light would travel in 1 second, which would be slightly less than 300,000 kilometers, then we could just take a coulomb and compare it to that distance, and we would come up with a diameter of each individual electron. By definition, we would have an exact diameter of each electron just simply from knowing the speed of light and having a very good definition of Coulomb's law, how many electrons exactly went by there. So increasing the voltage is it is going to do nothing more than increase the pressure of the electron, and you may say it should speed it up. And the electron can only speed up if, this gets a bit more complicated because it has to push more electrons out of the way. So you can push more electrons per second past any given point by increasing the voltage, and we'll call that the amperage. But if there's enough resistance ahead, then, and it was infinite, then we can start I think I'm losing myself and you trying to explain this, and it's not that important. What is important is that nothing can go from here to there except as fast as an electron can make it go there. And this comes to the Pauli Principle. The Pauli Principle is a rule in physics, and if you're into physics you know what I'm talking about, where no two things can be in exactly the same spot at the same time. So nothing can be where an electron is unless an electron gets out of the way, moves aside, or passes that energy in some sort of way, either through increased spin, decreased spin, or moving out of the way. So like it might want to get out of the way or ride over another wave that's going by. Can you see it riding? The gravitational wave going by. The electron ain't going nowhere, but it's riding a wave that's going by, which is providing more pressure upon the bottom side of it than the pressure that's up here. So the Pauli principle is involved in the speed of light, in that electrons cannot occupy the same space at the same time. And electrons don't like being where other electrons are. If something is deemed to have a positive charge, it didn't gain something, it lost something. It's like if you think of the laws of thermodynamics, Cold never comes in. Heat always goes out. The energy is trying to die. Its energy decreases, so heat always goes out. And the same, now I've lost what I was trying to make a point of there. The same thing happens with whatever I was talking about. See how I lose it? Where am I up to? I'm up to 25 minutes, and my main goal here is to get you to think about the speed of light and the fact that we have a principle that says no two things can be in the same place at the same time, and electrons rule our universe. No information, the microphones won't work, the camera won't work, your eyes won't work unless electrons transmit energy to your brain. And even though the speed of light may seem really, really fast, because that's the way you think about it, the speed of light is still the same at the atomic level, except that the way you think about time is different. If you lived on a carbon atom, you would probably be measuring time in picoseconds, because a second would just be too long a period of time to make any sense, except talking about months or years of time as you would view it if you were living at the atomic level of reality. And I lost myself, and I'm up to 26 minutes. So the whole point of all of this video is that I'm continually trying to find different ways of reaching a different audience to think about what is it that actually causes the speed of light. You can come up with the Planck's constant, and that really the smallest wave, no matter how small you go, will still have a number. And when you start looking at Planck's constant and you look at coulombs, you'll start noticing that the number of zeros are in the same number of zeros. So it's only logical to think that the measure, we used to have a platinum rod in Paris which defined what a yard was. We don't really need that anymore. But when we need a constant which sets all of our reality, it's staring us in the face every single day. We use it every single day. Quantum physics uses the energy and motion of electrons, the quantum leap, all of that. The speed of light is how fast energy can get from here to there. And it's as fast as an electron can move. And then you'll say, well, doesn't that mean light speed varies? Well, it doesn't really. When you really start thinking about it, anything which is smaller than the electron still has to get from here to there, and because of its physical size and following all the same laws of flotation and resistance, it can't get, no matter how small it is, from here to there any faster than the electron will allow it to, by either spinning faster or getting out of the way in one way or another, away from any other force trying to push the electron, which ultimately has a resistance related to the Planck constant, which is why you can't exceed the speed of light, because, well, you do seem to exceed, you don't really exceed the speed of light, but on a large scale it seems hard to go faster than the speed of light, simply because you have to push, for every electron you're trying to move forward in your mass, you have to push an equal number of electrons out of the way per unit of time, and the more of them you want to infinity you want to push out of the way, you just can't do it. You can never. It's quite probable that we could get to 50% of the speed of light, but after the 50% mark, it becomes meaningless anyway, because you're moving so quickly that you have to deal with the motion of all the other planets and everything. So warp speed is probably closer to 50% of the speed of light than it actually is to the actual speed of light, because then you would be on the inclined plane of the bell curve of all the resistances. And if you're seriously into physics, maybe that'll make sense to you. If you aren't, it doesn't matter. The whole gist of this whole long thing is to get you to think about the speed of light. Why exactly is it the speed of light? And the Pauli Principle, that's how I rickrolled you into this. You probably thought, what the hell is this about? So the Pauli Principle dictates that no two electrons can be in the same place at the same time. Electrons are mainly indestructible. Positive charges are simply a lack of electrons. A proton is missing one electron's worth of energy it wished it has, but it can't seem to totally get together with an electron unless it's in atomic form as hydrogen. It just doesn't seem to be able to make that fusion. And if the electrons in hydrogen could fuse into the nucleus, we would come up with a proton, and it would actually release energy. So if we could find a way to convert hydrogen into neutrons, we would get at least one quantum's worth of energy for every single hydrogen that converted into a neutron. And then the neutrons, we'd have to learn how to deal with them, and why did we create them in the first place? I do go on and on, don't I? Was this interesting or not? I forget the camera's up there. I'm staring down at me on the screen down there. Sorry about that. So I'm Terry David Silvercloud, and I'm going to be 74 years old tomorrow, and I'm trying to get you to think about the speed of light. I'm going to put my arrow on the red button there, and I'm going to say 5, 4, 3, 2, 1. Bye-bye.